So, the second lesson is looking at the life cycle of stars. Now, we want to pick a star that's going to be around for a long time, hopefully billions of years, so we don't have to move again. So it's important to know, is a star early in its life, middle, or late in its life? And what's going to happen to our sun when it basically runs out of fuel? So today we're going to look at the life cycle of stars. So, stars are born in what are called a stellar nursery or a nebula. And a nebula is a cloud of dust, hydrogen, helium, and other gases. And we think a lot of nebulae are formed from the remnants of dead stars, in fact. So stars may actually make other stars. In fact, we know everything heavier than hydrogen is made in a star, which means you are basically made of parts of a star. You're made of star stuff. So a nebula is a cloud, and what happens is, over time, gravity pulls bits of the cloud together. And as the bits get bigger, they get a stronger gravitational field, which pulls more stuff, which gets a stronger field, which pulls more stuff, which gets a stronger field, until eventually you've pulled enough stuff that you get that force that you need, that pressure, that actually creates fusion, which basically ignites the star, and it turns on, basically, blows off in an explosion, blows off the rest of the nebula around it, and you basically have a star, and then what's left becomes the solar system. So, stars are born in a nebula from clouds of gas. So, as I said, they contract because the gravity and the pressure gets bigger. Once it gets to 15 million degrees, they turn on. So, for example, one of the most famous nebulas is called the Horsehead Nebula because it kind of looks like the head of a horse. And, we think there are actually thousands of stars being born in that nebula. So, once fusion starts, that stellar wind starts, and it blows off the excess dust from the star. We think that's what the planets are made of. They're the remaining things that are a little too big to get knocked off, and then they start collecting what's left. And over time, it seems like most stars do have a solar system of planets around them right now. So, our star is now what's on the main sequence, that line on the Hertzsprung-Russell diagram, where it's stable and reasonably constant. It gets slightly hotter, slightly colder, slightly bigger, slightly smaller, but it stays pretty constant. And we think our sun can stay constant about 8 billion years. And we think we're about halfway through that. So we've got about 4 billion years left on our sun. So we don't need to leave anytime really soon, but as our sun gets bigger, it's going to get hotter. And we think in about 200 million years, in fact, Earth may be outside the Goldilocks zone of our sun, and we may need to move somewhere. Not ideal. But again, a couple 100 million years, I think we can figure it out by then. So the trouble is, if you have a fast-burning blue star or a really hot star, they basically burn through all their fuel really fast because they're really hot, so you have to burn fuel faster. And they only can last for 1 million years. So in fact, most blue stars you probably wouldn't get life around because it wouldn't have time to develop. I mean, it's taken 4 billion years to get to us. So if a star could only last for 1 million years, it's probably going to burn out. So a blue star, maybe not a great choice because it's not going to last for as long as a yellow or a red star. So, when stars die, stars run until they run out of fuel. Then they turn off. Now remember, I said in the last lesson that stars are constantly in a state of basically expanding and contracting. You have gravity and fusion fighting each other. Gravity wants to pull it together, fusion wants to push it apart. And what happens is, if they run out of hydrogen, the core basically runs out. There's no more force pushing it out, so it collapses inward. As it collapses inward, as the core collapses inward, it gets hotter, and then eventually it gets hot enough to start fusing helium into carbon by pushing helium atoms together and fusing them into carbon. The outer shell still has hydrogen, so the outer part of the sun still has hydrogen, so it keeps fusing, but not at as big a rate because it's not as hot. So the outer part of the star expands, creating the red giant or supergiant, but the core actually contracts because it's now fusing heavier elements which you don't get as much energy from. And the core keeps fusing until it hits lead. And lead is the stopping point because it takes more energy to fuse into lead than you get out of lead. So as soon as it hits lead, the star core, the star basically stops pushing outward instantaneously and the star collapses. And what happens depends on the size of the star. So, sun-like stars, stars like ours, basically follow one path. Smaller stars, huge and giant stars follow a different path when they run out. So they both start off the same. They both become, our sun will become a red giant. A big star would become a red supergiant. And then what happens is when the core collapses, it's not really pushing the star out as much. The star is sort of drifting apart. The star just basically keeps drifting apart. So what will happen is the sun will swell up to a red giant. By the way, Earth will probably be about there when it's a red giant. We'll probably be inside the sun, so we want to be gone before then. Then when it dies, it'll just, the outer part will drift apart, and what you'll basically have left is that core of iron, which will be white hot, and that's what we call a white dwarf, and it will eventually just cool off as it radiates energy into space and become what we call a black dwarf, which is basically just a ball of iron floating in space. Possibly useful to some interplanetary miners, not really useful to us anymore. So one thing you have to watch, there are two things called dwarf stars. One, dwarf just means a small star. So a dwarf star, a white dwarf and a black dwarf are basically dead remnants of stars. A red dwarf is an active star, but it never got big enough to basically be anything bigger. Okay, so a red dwarf is not a dying star. A white dwarf and a black dwarf are. Not really a great name, but unfortunately it's the one they picked. So, as I said, once the core hits lead, it can't undergo fusion, so you get a white dwarf, right, and then it eventually just cools off and becomes a black dwarf. The rest of the star floats away and becomes what we call a planetary nebula. Again, no planets in it, we call it a planetary nebula. If you're a giant stars are cooler because a giant star is basically going to explode because there's so much energy and so much mass in the outer part that when the core stops, the outer part actually contracts in about, a millionth of a second. The entire star collapses and then it rebounds into a huge explosion called a supernova, which blows away all the outer layers. And what you're left with depends on if it was big enough or really big. So, a supernova, and by the way, this is a really cool actual photograph of a supernova from the Hubble. You can actually see the explosion and the shock wave. Sometimes when the star collapses, so if in a supernova, that core will keep collapsing, and even the forces that hold atoms together aren't strong enough to counteract gravity. So it literally pushes the protons and electrons together in every atom, and when you stick a proton and an electron together, it actually becomes a neutron. The charges cancel out and it becomes a neutron. So what you get is, you get this ball of neutrons that are rapidly spinning, because as it contracts, the momentum switches to angular momentum, which makes it spin. So you have this rapidly spinning ball of neutrons, and it's solid. It's not like a normal atom where basically most of it is empty space. It literally is just neutrons smashed together. It's so heavy that if you were to take a spoonful, of neutron and drop it, and believe me, you wouldn't have a choice, it would actually be heavy enough that it would fall straight through the Earth, burrow right through the Earth, come out the other side, get caught by the Earth's gravity, come right back, and basically Swiss cheese the planet from a teaspoon of neutron star. That's how heavy they are. Think of something that has the mass of the sun, but is basically, you know, a kilometer or two in size. Okay, it's crazy. So neutron stars we can actually see because as they spin, they give off radiation. They can either be continuous or they can be pulsing. By the way, you've heard of a pulsar. That's basically what a pulsar is. It's a neutron star that gives off pulses as it spins towards us. We think because they may rotate along more than one axis. So every now and then that jet will hit us. So that jet hits us and then it goes around, then it hits us again. That's what we think causes these pulsars. So we see pulses. If we were right in line with the neutron star, we would actually see a constant stream. But from the pulses, we can actually tell how fast it's spinning, which we can find its mass from and also do all sorts of cool math with. Now, if they're the really big stars, sometimes the star is so heavy that not even the neutrons can, the force of gravity is stronger than the force keeping the neutrons apart, and they collapse together. And what that makes, we really don't know because it breaks math. It shouldn't exist, but we now know. And in fact, this is the cool thing. You are the first class I've ever taught where I can say definitively black holes exist because we now have a picture of one. We're not sure what they are because it shouldn't work, but it does. So we don't know what's inside a black hole because a black hole is black because its gravitational field is so strong that not even light can escape it. Light gets sucked into black holes. In fact, the circle you were seeing when you looked at that black hole picture is actually light from behind the black hole getting spun around the black hole so that you're looking at the back of it, which is really, really weird. So not even light can escape, and the way we found black holes, first off, the math said they should exist, even though the math of what was inside them said they shouldn't. People tried to find them for a long time. We found things that looked like black holes because we saw stars orbiting seemingly empty space, which meant there had to be something really massive there to make it orbit. And fortunately, the black hole picture that came out last year, we now actually have visual evidence of a black hole, which is really, really cool. But as I said, what's inside, we don't know because light can't escape. And the math inside a black hole is actually really, really funky. By the way, if you want a really good view of it, I really recommend watching Interstellar. It is the best example of a black hole we had. And in fact, the black hole it uses ended up looking exactly like the one the picture created, which is really, really cool. Because we were just guessing when they made that movie. That was based on the best science at the time of what we thought a black hole would look like. So why scientists were really amazed with the picture was it was exactly like we expected it, which was really, really cool to find that, the math for something that shouldn't even exist, but the math tells us it should, and the math tells us what properties it should have. When we actually look at it, it's right there, which is why scientists got so amazingly interested in it. So that's the end of a star. Not the end of our star, we're going to become a white dwarf, but that's the end of a really big star, is a black hole. So to recap, stars start their life in a nebula, a cloud of dust. They contract till they turn on for fusion. Most of their life is in the main sequence. When they start running out of hydrogen, they start fusing other things, become red giants or supergiants, and then either float away in a planetary nebula, making a white hole like a white dwarf like our star, or they explode in a supernova, making a neutron star or a black hole if they're bigger. All right, I hope you had fun, and I'll see you next time.